Hi everyone, I'm Kajal Mahendru. I hope you all are preparing well for upcoming CSIR NET and GATE exam. So I thought to make a video on one of the trendy topic in solid state physics that also comes under statistical physics, that is density of states, dispersion relation for electron, relativistic and non-relativistic both cases, photon, phonon, magnon, and dependence of various physical quantities like number, density, temperature, pressure, energy, specific heat, etc. And we will solve each and every question right from GATE 2010 and CSIR NET 2011 till now from this concept, and many of the questions have been asked from this concept, and I will not go to the depth of this concept. As for in-depth knowledge, I will link some YouTube videos or playlists for better understanding. And in this video, we will learn some tricks to solve such kind of questions, so that you could save your time in exam. And as you all know that each and every second is precious, so let us start. So we all know that the dispersion relation is the relation between the frequency or the energy with the wave number, and for non-free non-relativistic electron, the dispersion relation is that E is equals to h bar square k square by 2m. You all are familiar about this. For relativistic electron, E is equals to h bar k c. H bar k is momentum. Actually, in this case, we have taken we have assumed that the kinetic energy is greater than the rest mass energy. So from that, we know that E is equals to square root of pc whole square plus m naught c square, the square. So from that assumption, this relationship has come, that the kinetic energy is greater than the rest mass energy. For photons, the dispersion relation is omega is equals to c times k, where c is the velocity of light or the photon. For phonon, the dispersion relation is omega is equals to vs times k, where vs is the speed of sound. And for magnons, the dispersion relation is omega is equals to a times k square. So clearly you can see that s is equals to 2 for non-relativistic electron and magnon, that is 1 and 5 point, and s is equals to 1 for relativistic electron, photon and phonon. So uh, here I have discussed some parameters and their dependencies, uh, like density of states is dependent on uh, the omega, that is frequency, as as omega raised to power d by s minus 1, and where d is equals to dimension, that in what dimension we are talking about. uh, and if we talk about internal energy is directly proportional to the temperature raised to power d by s plus 1. For specific heat, we know that specific heat is du by dt. So clearly, cv is that is specific heat is proportional to T raised to power d by s. Similarly, entropy, how these relationships have come, this you can for the derivation of these things, you can refer to Quanta Institute's statistical physics lectures. I will provide the link in the description box. Similarly, for number density, uh, its dependency on temperature is as follows, and similar dependencies of other quantities. You can note it down in your short notes or like in whatever notebook. So so that these quantities are really these relationships are really helpful when you will solve the questions relating to that. So uh, here is one more table which I think would be useful to you. For non-relativistic free electron, I have made a table on 1D, 2D and 3D cases. Uh, and Fermi energy and the formulas of various quantities, for EF Fermi energy, the formula for 1D case is h bar square k square by 2m. Here k is equals to n pi by 2l for 1D case, and for 2D case it is 2n pi, k is equals to 2n pi by a. So the Fermi energy will be h bar square by 2m times 2 pi n by a. And similarly for the 3D case, I think you should remember these things. This will save your time in the exam. So let us discuss the questions. You will understand these concepts. So first question is that two-dimensional free electron gas, um, the number density and the Fermi energy are related by. So in the previous table, uh, the relation is already given. So here also I will solve. We know that EF is equals to h bar square by 2m to n pi by a. Now n by a is the number density, that is number of free electron per unit area. In 2D case this is number density. So if you will solve, option B would be the correct answer. The next question is that you have an ideal Fermi gas in 3 dimension, and you have to find out the dependence of Fermi velocity with electron concentration. So you can also solve by yourself and pause this video and then see the solution. So we know so here you can see that we have three dimensions, right? So d is equals to 3, and Fermi gas is there, so s is equals to 2. We have already discussed that for free non-relativistic case. See, you will take non-relativistic case only unless it is given. If it is specially given that it is a relativistic case, so then you will take s is equals to 1. Otherwise by default s will be equal to 2. S is equals to 2 for fermions, for the free electron gas. So as we know that Fermi energy is related to number density as n raised to power s by t. So plugging the values, the Fermi energy will be proportional to n raised to power 2 by 3. Now Fermi velocity, we know that it will be Pf divided by m, and we know that Pf is under root 2 me. So Vf will be proportional to Ef raised to power 1 by 2. So from the first equation, the Fermi velocity is proportional to n raised to power 1 by 3. So option D would be the correct answer. Then in this question, GATE 2015, energy dependence of density of states for a two-dimensional non-relativistic electron gas. Okay, so you have two dimension. So n is equal, s is equal, sorry, d is equals to 2, and you have non-relativistic electron gas, so s is equals to 2. So we know that density of states in that table. I have also said that note down all those dependencies. So we know that density of states is proportional to e raised to power d by s minus 1. So plugging the values, you get the e raised to the density of states proportional to e raised to power 0, so n is equals to 0. So the value of n is 0 in this question. Now gate 2015 again, two questions from gate has come to a same concept in 2015. You have Fermi energy of gold. You have to find out the number density. So mass of electron, Planck constant, and other 1 electron volt is given, the conversion is given. So in this question we know that Fermi energy for an free electron gas is h bar square by 2m times uh, k square, also as k is equal to 3 pi square n raised to power 1 by 3. So just putting the values, and as in gate the, and also now in CSI net the calculator has been provided, just plug the values, you will get the answer. So the answer would be 5.9. Then now this question is of gate 2016, that you have to find out the Hall coefficient dependency on Fermi energy. So as we know that Hall coefficient is 1 upon Ne. So we know that again repeating that EF is proportional to n raised to power s by d. So plugging the values, we get EF proportional to n raised to power 2 by 3, and n dependent on EF as 3 by 2. So from the first equation we get RH is proportional to 1 by EF raised to power 3 by 2. So dependency of RH, RH and EF will be RH proportional to EF raised to power minus 3 by 2. So option C would be the correct answer. And the next question is that consider a two-dimensional electron gas with density 10 raised to power 19 meter square, meter inverse square. So Fermi energy we have to find out. So clearly we know, just you have to plug the values. It is same like the earlier question. In the earlier question they were asking about the number density, and the Fermi energy was given, and in this question the Fermi energy they are asking and the number density they have given. Just they have also changed the dimensionality. So we know, just you have to put the values and the answer would come out to be 2.34. Here I have also written the kf values for free electron. Then sorry, in here I have done a mistake. Here the power is 1 by 2, and here the power is 1 by 3. So in gate 2000, this is a question of gate 2019, that energy and wave vector dispersion relation is given to you, that E is equals to C times K. So here you can see that S is equals to 1. Here you can see that S is equals to 1, and 2 dimension is given, so D is equals to 2. DE is proportional to E raised to power D by S minus 1. So just plugging the values you get B is equals to 1. So this is just a direct result. that you have a dispersion relation. This is the question of June 2012 net JRF. Dispersion relation has been given to you, and they are asking that density of states is proportional to. So clearly it is proportional to d by s minus 1, e raised to power d by s minus 1. So option B is the correct one. So now in this question, they have asked you about energy dispersion relation of a two-dimensional electron system, and E is equals to U h bar k. So S is equals to 1 and D is equals to 2. So density of state depends upon energy. So uh, just plugging the values. Uh, this is same as I think the earlier question. So now this question, that pressure of a non-relativistic free Fermi gas in three dimensions. So non-relativistic free Fermi gas, so S is equals to 2, 3 dimension, D is equals to 3. Now I have written, they are asking pressure at T is equals to 0. So T is equals, pressure at T is equals to 0 is called 0 point pressure. Just like energy at T is equals to 0 is called 0 point energy. So same as 0 point pressure. So we know that 0 point pressure depends upon the number density as S by D plus 1. Uh, n raised to power s by d plus 1. So just plugging the values, we get 0 point pressure proportional to n raised to power 5 by 3. So option A is the correct one. Next question is of CSIR night June 2015. Uh, what you should do, just pause the video and solve it by yourself and then check the solution. This will help you, I think, a lot. So here in this question, ek relationship is given. So E is proportional to k raised to power 1. So S is equals to 1, 2 dimensional. So D is equals to 2. This is, I think, a repeated question, and this question is same as the last to last question. So DE is proportional to E raised to power 1. Then this question, consider electrons in graphene and okay, a planar monatomic layer of atom. So I think it is two-dimensional case. So and E is proportional to k raised to power 1. So D is equals to 2 and S is equals to 1. So we know that Fermi energy is proportional to number density as S by D. Just N is replaced by rho in this question. So just plugging the values, A option would be the correct one. Then this question is of December 2017, and dispersion relation for a spin half fermions in 2 dimension. So dispersion relation is already given to you. So S is equals to 1. Clearly you can see from the dispersion relation, and they are asking about the dependence, about the number of particles per unit area, that is number density. So see here in the options you can clearly see that the power of EF Fermi energy is different in all the all the four options. So solving that would be very a tedious task, I think. Just plug the values in the formula, so you will save a lot of time. Here also the method 2 has been given. You can also solve by this method, but as you can see, this is a traditional method. So this would save your time. So I hope that this video would be helpful to you, and all the best for upcoming exam. Thank you.